Hello. So, last class we have learnt higher order methods and also higher order equations. So, that is second order initial value problem has been solved by reducing it to a system of coupled first order equations. So, now when we define a method, how do we know that what is the error? Suppose somebody gives this is a method, how to compute the error? And of course, we discuss in this lecture how a particular method is stable and then whether the particular method gives convergent solutions and what is the reference equation with which we analyze this process. Okay. So, let us discuss first how to compute error given an approximation. So, how to compute error for a given approximation. So, let us say we have the following approximation. So, I am not naming the method, what is this method called, etcetera. Suppose there is some given. So, therefore, so these are the weights k 1, k 2, w 1, w 2 are the weights 1 by 4 and 3 by 4 and k 1, k 2 are defined like this. So, now we would like to know what if we approximate by this formula for a given IVP, what should be the error. Okay. So, how do we do it? As I mentioned, we have to make the expansion in terms of h and then we have to expand the Taylor series and try to compare. Okay. So, let us try to do that. So, we have y n plus 1, so y n plus h by 4 f plus 3 h by 4 Okay. So, now this has to be expanded in powers of h. So, this one f of x and y n plus the increment is this. So, 2 h by 3 dou f by dou x plus increment with respect to this 2 h by 3 f. So, these are the first order terms plus second order terms, square of that so 2 times plus okay. So, this is our expansion. So, we have 3 by 4 and 1 by 4. So, h f plus h square by. So, h square terms. So, one term h square term is 3 gets cancelled and 2 by 4 is half and we have then the next term from here we get plus h cube h cube by 6 okay. So, this is our H expansion. Then we have to compare this with Taylor series expansion, and you can see in Taylor series these terms exist. So, first term approximates y of x n, second term, third term. So, then if you make equal coefficients of h power 0, h power 1, h square. So, then we get error starts from okay. So, for any method we try to determine using this method this way. Okay. So, we know x and y n. So, this f we know. So, the error is of order h cube, and hence the method is of order h square. Okay. So, that is second order. Okay. So, now as I mentioned, we have to discuss stability and convergence. So, what do you mean by stability and convergence? Okay. So, let us try to understand this with respect to a reference equation. So, what is the reference equation? What is our reference equation? Y dash is lambda y, y of x 0 is y 0, x. So, this is our star, and exact solution of star is y of x equals to c times. So, if you use this initial condition, we get y 0 e power lambda. Okay. So, this is our exact solution, right. Now, in order to compute y of x at so, that is the idea, right. So, what is y of x 1? y 0 e power lambda x 1 minus x 0. So, that is y 0 e power lambda h, because x 1 minus x 0 is okay. Then y of x 2 is y 0 e power lambda x 2 minus x 0. So, y 0. So, this is y of x 1. So, we can generalize okay. So, now in order to compute the solution, we have to compute this. difficult to compute, but difficult to compute means how difficult? Okay. So, how difficult? So, the idea is approximate e power lambda h suitably. Okay. Approximate suitably, right. So, how do we approximate? Okay. See, in case of Euler method, let us talk about Euler method y n plus h f of, okay. And what was our reference equation? Lambda y. So, this is our f of x y. So, therefore, this reduces to y n plus lambda h y n. So, this is 1 plus lambda h y n. Okay. And what was our approximation? Y of x n plus 1 is y of x n e power lambda h. So, y n is approximating this, that means e power lambda h, 1 plus lambda h is approximating this. So, therefore, this is Euler. So, for Euler method, e power lambda h has been approximated by 1 plus lambda h plus order of, okay, right. Suppose let us take Taylor series method. Okay. So, take y n plus 1 is y n plus h f of x n y n h square by 2 factorial. So, y double. So, that is dou f by dou x So, now this with the reference equation, that is y dash equals to lambda y, which was our f. This reduces to y n plus, our f was lambda y n, okay. Dou f by dou x, okay. F lambda y square plus order of h cube. Okay. So, this is 1 plus lambda h plus lambda square plus. So, when I mentioned there is a lambda sitting, when we substitute this, definitely there will be a lambda cube. So, that means e power lambda h has been approximated by okay. So, this is the approximation, right. So, let us call this approximation Okay. So, let us call this approximation for. So, that means given y n approximation is as follows y n So, this is what is happening. Okay. So, now we have to discuss stability, right. So, what is round of error? When you have an approximation, there is a value which is machine value plus r is y true representation. Okay. So, this is the round off, because of the machine restrictions we are rounding off, and truncation error. So, y true representation plus t is y exact. So, that means we are expecting something exact, but y we are representing by an approximate formula and we are throwing some terms. So, that is the truncation error. Okay. So, y n plus 1, y n plus 1 is y of x n plus 1 plus where p is order of the method. Okay. Because this approximation is up to something, and that is the truncation error. Okay. So, if the method is pth order, some theta. So, this is local truncation error, more generalization. Okay. Right. So, now if you say this is up to some approximation, okay, some truncation. So, now let us say we compute y 1. So, we have thrown t corresponding to y 1. Now, compute y 2. So, we use y 1. That means, whatever you have thrown t at in computing y 1. So, that will be still sitting in the system, and then we have to understand what kind of impact it is creating. Okay. So, let us talk about stability of a method. So, formal definition, it is nothing but how the error is playing a role. A numerical method is said to be stable if the effect of any single fixed round of error is bounded independent of the number of mesh points. The numerical method is said to be stable if the effect of any single fixed round of error is bounded. That means, the effect of a round of error is bounded, means it is not really growing, and is independent of the number of mesh points. This is another important parameter. So, or if for every epsilon greater than 0, there exists delta of epsilon such that for two different numerical solutions y n and say y n bar, the difference is less than epsilon whenever the corresponding initial conditions for every h. Okay. So, this is very important. For every epsilon, there exists a delta which depends on epsilon such that, so see the scheme is same. We are talking about two different solutions with two different initial conditions. So, now as long as the difference is delta of epsilon, the approximations should not be deferred by large quantity, and this must hold independent of the mesh size. Okay. So, now when you are approximating with what you are, so for example, in Euler method we have seen, in Euler method we have expanded and then considered only first two terms. So, we got 1 plus lambda h. Then Taylor series, it depends on, suppose you are using 3 terms, then we get 1 plus lambda h plus lambda square h square, and then if you use more terms, that means your exact solution which is of the order e power lambda h, we are approximating that, right. So, a comparison between these two must be made. So, that means compared to what you are approximating e power lambda h, it should have been e power lambda h, but now you are approximating by something. Okay. So, also there should be a comparison. So, let us do that. So, let us call our approximation okay. So, which means, so this is a true exact plus epsilon n plus 1 is e power lambda h y of x n plus y n plus 1 is exact plus epsilon n plus 1 at n plus 1 stage. Then we have this approximation, then y n is y of x n plus epsilon n plus 1. So, this implies lambda h y of x n epsilon n. Okay. So, now this is minus how did we write this? Y of x n plus 1 is actual solution is e power lambda h into y of x n. So, I am writing y of x n plus 1 is replaced by e power lambda h y of x n. So, we take common plus Okay. So, now what is this tells? This is exact, but this is the approximation, right. So, this is nothing but local truncation error. Okay. So, now how can you minimize this? You can minimize this by approximating e power lambda h more closely with e power lambda h. So, that means this can be made small by suitably approximating okay, that means suitably choosing E of lambda h. You choose a better E of lambda h, it is close to. So, you can see Euler method 1 plus lambda h, whereas Taylor series with more number of terms, it is more close to e power lambda h. So, in that sense. Then what about this? See, this is approximation and this is the error at n stage, and that is contributing to error at n plus 1 stage. Therefore, this must be the propagation error. So, what is the propagation error? This is the propagation error from x n to x n plus 1, and this is inherited. Okay. So, error at n plus 1 stage consists of two parts. One is local truncation error, which is due to the approximation. The better you approximate close to e power lambda h, the minimum the local truncation error. Other is the propagation error. The error at nth stage has been magnified by this factor. So, now one can guess easily how do you minimize this? Yeah, as long as your approximation is not magnifying, because this is the factor error at nth stage is magnified by this. So, when do you say the propagation error will diminish? If E of lambda h is not magnifying it to a large extent. Okay. So, we discuss this is the stabilizing factor, because what is the stability? Stability means I mentioned, see, you are computing, you have defined a process, okay. It is a single step process. To compute a value at some stage, you require value at the past one stage. So, now you it is a recurrence process. So, you compute y 2 and then use it to compute y 3, then compute y 4 using y 3 and so on and so forth. So, whatever the errors existing at one step ahead, that has been incorporated into the higher steps, right. So, now you have to control this. So, this can be controlled only when your approximation is playing some role. Okay. So, we define that now. Okay. So, the definition. So, a numerical method of the form is called absolutely stable if what? Yeah, there you are. This is the magnifying factor. So, this should not magnify to a large extent. That means, yeah, the modulus must be less than or equal to 1. So, if okay. Right. So, that means E of lambda h should not grow faster than, because your approximation is making it magnified, the error, definitely the method is not stable. Okay. So, the comparison is between this and this approximation. Okay. So, hence a numerical method of the form is relatively stable if if you can ensure that this is always less than or equal to 1, then it is absolutely stable. That means, whatever the errors which have been carried at nth stage, so they are not magnified beyond magnitude of less than 1. So, the error is going to be bounded. One can ensure that at next level the error is bounded. Okay. So, this is absolute stability, but another is compared to what? This approximation is compared to e power lambda h. So, therefore, so this is, if this is less than or equal to e power lambda h, so then it is called relatively stable. Okay. Okay. Right. So, take Euler method, y n plus 1 is y n plus h which is equals to y n plus h lambda y n. So, therefore, E of lambda h is 1 plus lambda h. Hence, mod E of lambda h is less than 1 implies so that means this is the region of absolute that means the method is going to be absolutely stable as long as you choose step size such that lambda h falls in this range. Now, what is lambda? Lambda is coming from our reference equation, but we have more general form, that is y dash equals to f. So, that means at some later stage y dash equals to f. So, why are we talking y dash equals lambda y as a reference equation, whereas we need for a more general case. So, we will do it little later. Okay. What is the connection between this? Why do we take such a reference equation when we need a more general case of f? Okay. So, then Taylor's method, suppose up to 2 terms, 3 terms. So, this implies so this is first order, second order, then one can also obtain third order. Okay. Right. So, one is propagation error, another is local truncation error. Then we talk about absolute stability with respect to this factor, and we talk about relative stability with respect to this distance between these two. Okay. So, that is what we have done, right. So, now we go back to this question. Why did we consider y dash equals lambda y when we need y dash equals to f? Okay. So, y dash equals to lambda y as the reference. Okay. Right. So, what we are doing? We are considering a particular point x and y n, and we are trying to analyze for that value what happens to the approximation. So, that means we need to predict the behavior of the IVP y 0 in the neighborhood of a point. So, this is what we are trying to analyze, okay. But with respect to the general case. Then what we do is linearize. Okay. So, how do we do it? F of x y around this point plus this is multiplication plus okay. So, this equals y dou f by dou y, okay, plus f, okay, minus y bar dou f by dou y plus okay. So, now this is any nonlinear function, but we have linearized it with respect to the dependent variable. So, that means with respect to the dependent variable, the equation has been linearized, f has been linearized. Okay. So, now with this f, your y dash equals to f can be written as this becomes y dash equals to lambda y plus c, where lambda equals to lambda y. So, lambda is dou f by dou y and c okay. So, where of course, where x is in x not b. Okay. So, this can be transformed using c by lambda, whose solution is okay. So, that means so this is so we try to analyze the behavior of the solution, and it depends on certainly the lambda, okay, and where lambda in turn depends on f. Okay. So, let us see for example, say y dash is x square minus y 1, then analyze the behavior of the solution around say one minus 1 and say 0 2. So, now what is our f? Therefore, suppose let us have so this will be minus 2 y. Okay. Now, dou f by dou y at 1 minus 1 will be minus 2 y at 1 minus 1. So, that will be 2, which is lambda positive, dou f by dou y, sorry, around 0 2 will be minus 2. So, that will be minus 4, which is lambda. So, that means this f around this point the solution behaves like this, and whereas around 0 2 the solution behaves, it decays, and here it grows. Okay. So, our question of why the reference equation, that means the solution, overall behavior of the solution for the nonlinear case can be interpreted by linearizing f and estimating the behavior of the linearized case in this sense, because this is a more general form. Hence, this is our reference equation. Okay. This is our reference equation. Okay. So, we started with stability. Okay. So, numerical method is said to be stable if the effect of any single fixed round of error is bounded independent of the number of mesh points. Okay. So, that means the approximation should be bounded by epsilon whenever the initial data is within the range of delta, which depends on epsilon, and then we have approximated given solution of the given IVP. Then we introduce the error at n plus 1th stage. So, that will come from two different parts. One is the inherited, which is due to the error at nth stage, and the other one is due to the approximation. And the better you approximate e power lambda h, you get the better minimum local truncation error. So, now once we have these two parts, this will define absolute stability. Why absolute stability? Whatever error at nth stage, it is magnified by this factor. So, as long as you are controlling this, there will not be much inherited error. So, therefore, you can assure that absolutely stable, whereas this compared to what? How far you are from actual e power lambda h, this is your approximation, how far you are. So, that will tell relative stability. So, therefore, a numerical method of the form this is called absolutely stable if this is the condition, and relatively, so it should not grow faster than this. So, that will introduce numerical method of the form is relatively stable if this happens. Okay. So, for a particular method, single step method, these are important criterion, absolute and relative. Okay. So, let us take one of the RK methods and try to estimate the condition for absolute stability. So, for example, we take Hahn method. Okay. So, the Hahn method So, we have Horn method y n plus 1 is y n plus h by 4 this. Okay. So, this is so Horn method h by 4. So, k 1 is f of x y plus 3 k 3. So, 3 k 3 that is f of x plus 2 by 3 h k 2. So, y n plus f plus 3 k 2 is so, now with our reference equation y dash equals to lambda y, this becomes y n plus h by 4, f is lambda y and this is f of so y plus 1 by 3 h, f is lambda y. Okay. So, we have to f of y plus lambda h y so this is y n plus h by 4 lambda y plus 3 f of okay, y plus 2 h by 3. Now, this is our y. So, what is f? Lambda y. So, therefore, lambda y plus okay. So, this is y n plus h by 4 lambda y and this is our y. So, lambda y must be lambda times so this is all y n now. Plus 3 lambda square 1 y comes out right. Oh, this multiplies only here. I am sorry, this multiplies only here. Okay. So, lambda y plus 3 lambda y plus 2 h by 3 lambda plus 2 h square lambda square by 6 okay, and this is 1 y. So, this is for Horn's method. So, this is y plus h by 4 okay, h by 4 lambda plus 3 lambda 1 plus so if you make this 1, so this is which is slightly complicated. So, we can simplify a bit, and for absolutely stable we must be able to get a some a prime and b prime. Okay. So, this will give the interval of absolute stability. Okay. So, this looks quite complicated, but nevertheless attempting for at least higher order methods, you get an algebraic expression for the range to compute the interval in which the approximate method is absolutely stable. So, from that algebraic expression we can try to estimate the bounds. In some cases it is straightforward, in some cases it is quite tedious. Okay. But nevertheless, given an approximation, that means approximate method, we have learnt how to compute the corresponding error, and further we have learnt how to compute the absolute stability interval, and also with reference to the reference equation how far it is, how closely it is approximating. So, that is the relative region of relative stability. Okay. So, this will give a sensible idea about single step methods and how the stability and error are related. Okay. So, in particular for the absolute stability, the approximation what you are making, so that will play a vital role. Okay. So, we have learnt RK method, these are called explicit, because to compute n plus 1 we have passed one value. Okay. So, there are some implicit methods, but these are quite complicated. Okay. So, we will see how we proceed. Okay. Have a good day.